Hi, this is Mrs. Basin, and today we're going to talk about calorimetry, which is section 5.5. So we talked about in class how we can't know the exact enthalpy of reactants and products. We can only measure the change in enthalpy, or the delta H, through a process called calorimetry, which is measuring heat flow. So we can use something called a calorimeter, that is a piece of equipment that will measure that heat flow. So we're going to talk about two different types of calorimeters and how to do the calculations for each one of those. So when we're talking about specific heat, the first thing we want to look at is what heat capacity is. So heat capacity is how much energy we need to raise the temperature of a substance by 1 degree Celsius or 1 Kelvin. The specific heat capacity, or what we usually call just specific heat, is the amount of energy required to raise the temperature of 1 gram of that substance by 1 degree Celsius or by 1 Kelvin. So every substance has its own specific heat. So this is going to be a value that you will either look up or would be given to you when you were doing an experiment. So let's look at how we would actually do these problems. So we talked about using Q equals MC delta T in class. So this is the formula that we're going to use for this. So for this particular one, we know we have 250 grams of water. Its temperature changes from 22 degrees Celsius to 98 degrees Celsius. And then it tells us that the specific heat of water is 4.18 joules per gram degree Kelvin. So we're going to start by writing down what our mass is. So our mass is 250 grams. Our temperature, our initial temperature is 22 degrees Celsius, and our final temperature is 98 degrees Celsius. And remember, when we're looking at our change in temperature, we always take final minus initial. So that gives us a value of 76 degrees Celsius, or 76. And this, like we said a minute ago, this could also be joules per gram degree Celsius. So the fact that this is in Celsius is okay, because the difference is going to be the same. And then our final piece of information we need is specific heat, which is notated with a C. And that's 4.18 joules per, like we just said, gram degrees Celsius. So Q is what we're using as our variable for heat, or enthalpy. So Q equals MC delta T. Then we substitute in our values for all of this. So 250, 4.18, and 76. So our final answer here is 79,420 joules. And then if you wanted from here, you could change that to kilojoules. So everything is going to cancel out here, and I didn't put all the units in there because I was running out of room, but everything is going to cancel out here except for the joules, and that's going to be our unit that we measure, or our unit that we use to express heat. Okay, so like we just said a minute ago, we can use, there's two different types of calorimeters we can use. So the first one is called a constant pressure calorimeter. This is often called a coffee cup calorimeter because it's done in a styrofoam cup. There's a couple different variations on this. This particular one that you're looking at has two styrofoam cups nested together, again, to try to retain that heat and not have a lot of heat loss like we had with one of the labs that we did in class. You also notice it has a stopper on it. And then there's a place for the thermometer, and there's also a place for a stir. So you'll see different variations of this depending on what your particular setup is. What's going on here is you're carrying out the reaction in an aqueous solution. You can indirectly measure the heat change for the system. So again, we talked about you can't directly measure the heat of the reactants, the heat of the products, but you can look at the change in heat. So you're looking at the change for the system by measuring the heat change for the water in the calorimeter. So we'll look at that a little more here on this next page. So we talked about how the specific heat of water is 4.18 joules per mole Kelvin, or joules per gram degree Celsius. We can measure the enthalpy for that reaction using that equation we just talked about. So Q equals MC delta T. Now when you're doing a reaction like experiment like this, where you have the reaction doing one thing and the system or the solution doing something else, you have to remember that Q of the solution has an opposite sign of Q of the reaction. So like we talked about, that sign in this particular, when we're talking about thermochemistry, has to do with the direction of the heat flow, not the magnitude of the number. So here's our equation one more time. Our Q equals MC delta T. Q is our enthalpy. That's going to be measured in joules, or you can change it to kilojoules. M is the mass of whatever the substance is. So we're going to see in a minute here how if you have you're mixing two substances together, you have to take into account the total mass. C is our specific heat, and that's specific to whatever the substance is. If it's a reaction that's happening in an aqueous solution, then you would use the specific heat of water. And then delta T, like we said a minute ago, is the final temperature minus the initial temperature. Okay, so here's another example problem that uses the coffee cup calorimeter, or the constant pressure calorimeter. This says a student has 50 milliliters of 1 molar HCl and 50 milliliters of 1 molar NaOH in a coffee cup calorimeter. The temperature increases from 21 degrees Celsius to 27.5 degrees Celsius. We want to know the enthalpy change for this reaction. So this time, when we decide what our mass is, we have to take into account that we're mixing these two things together. So we have 50 milliliters, and like we said, we've talked about in class, 1 milliliter is about equal to 1 gram at room temperature of water, and we can use water in this case because these are aqueous solutions. So we have 50 grams of HCl and 50 grams of NaOH. So this would give me 100 grams of the substance that I'm reacting here. Then we also notice that the change in temperature goes from 21 to 27.5, so our change in temperature is 6.50 degrees Celsius. And our C, because we're using water, is 4.18 joules per gram degrees Celsius. So this is going to be Q equals MC delta T. So I have 100 times 4.18 times 6.50. And what I end up with here is 2,717 joules. Now when you look at this particular number is what happens to the solution. So if you notice, the sign of this is positive, which means the solution gained that much heat. For the solution to gain that much heat, that means that particular reaction was actually exothermic. So it released 2,717 joules for the reaction. So this is what we mean by looking at the difference between the solution versus the reaction. All right, the last type of calorimetry we want to look at is something called bomb calorimetry. So this is a little bit different setup. This is not something we can do in the classroom, or in our classroom. You can do this when you get to college. Most colleges have these. So what happens here is the sample is actually combusted, and then the heat is absorbed by the water in the system. You're still looking at a change in temperature, but this particular one is carried out under conditions of constant volume instead of constant pressure. So if you look at the setup is a little bit different. You have a motorized stirrer. You still have a thermometer so you can look at the temperature change. You can see the sample in there. You can see, though, that there's water surrounding the sample, and then there are electrical leads so that you can ignite the sample. Now when you have a bomb calorimeter, each individual bomb calorimeter has a heat capacity specific for that particular piece of equipment. So that is something that would have to be figured out ahead of time, or you would have to know that for that particular calorimeter that you were using. So this equation is a little bit different. This one you're solving for Q for the reaction, and so our formula is Q equals negative C cal times delta T. So delta T is still the same as before, final minus initial, but the C cal is that heat capacity value that you would be given, and it's negative already because that particular reaction that we're looking at is going to release energy, so that's why that value is negative. So let's look at what one of these looks like. So this one, it says we have 4 grams of methyl hydrazine. Now the other thing that's different here is the amount of energy that's released is for whatever gets actually burned in that bomb calorimeter. So the amount of energy released for this particular data that's given is for that 4 grams. So our mass, we're going to write the mass down even though we don't need it to start with. We're going to write down that there is 4 grams in that particular bomb calorimeter. Then it says the temperature increases from 25 degrees to 35.9 degrees. So that gives us our temperature change. So that's 14.5 degrees Celsius. And then the other thing it tells us that in a separate experiment, they figured out what the heat capacity of that calorimeter was. So it's 7.794, and this time notice it's in kilojoules per degree Celsius. So we want to know what is the heat of reaction for that combustion. So heat of reaction, again, that's just heat or enthalpy. And we want to know, this particular problem says, for a mole of this. So we're going to have to do two separate problems here. So the first thing we want to do is do our Q equals negative CCal delta T. So our CCal is given 7.794 times the change in temperature, which we figured was 14.5 degrees Celsius. So our Q for this particular reaction is negative 113.01 kilojoules. The negative means that that much heat was released when that substance burnt. But this is per 4 grams. So the question's asking for what is the heat of combustion per mole. So we're going to set up a little conversion down here. So negative 113.01 kilojoules per 4 grams. We want to know what it is per 1 mole. So I'm going to put 1 mole on the bottom, and I'm just going to do a molar mass conversion here. So methylhydrazine is CH6N2. So when I add all those up, that molar mass is 46.1 grams. So when I solve for that, it's it's 1,302 kilojoules per mole of methylhydrazine. So when you do these, you need to be careful about how you answer the problem. Some of them might ask how much energy is released for whatever it is you put in there. Some of them might ask per gram. Some of them might want you to go per mole.